and Yanis don't need any introductions. So let's just give them the podium. I should suggest that there will be a lot of coding introductions. So Tatiana, Anya, Justina, if you have any questions or if you want this to go a bit slower, just let us know, okay?
Okay.
Okay. So good evening, everyone. So for the sake of my presentation, I will turn off my camera and keep my voice okay like that. First of all, today I will present to you two technical documents. It is all written in Python, and it will show the results of data sent by Poland team for predicting GRACE data already. These are not so heavily commented. I maybe tailored them more to be more presentable, but during the last month, together with my very capable colleagues, we developed a short course on machine learning, which includes 4 parts. The first is setting an environment. The second one was a Python coding basics. Third one is data engineering, or preparation of data for machine learning, based on the real example. And the last one is machine learning and data visualizations. So I already have those packed and ready to go. Just one question for Tatiana, probably. As I understand, the data you provided is open access. Yeah, the one I will be presenting. Can I also share in that bundle, of course, this case study of Poland data, along with the data?
If I can answer this question, yes, all the data are freely available from GRACE or from satellite data or from models.
So, okay, so if I share this with other people, it is okay, yes? Meaning these documents, the machine learning process, along with the data itself. It's okay, yes?
I think yes.
Perfect. Okay, so let's begin. I will try to squeeze into 30-40 minutes. There are 2 parts. The first one is how to prepare data for machine learning or data engineering in general. Actually, it's the major part of all the process in ML, at my experience. The machine learning is, well, I would say pretty simple, but it's simple relative to the process of how to join, how to connect, and how to filter out and prepare data. So therefore, I split it into 2 parts. So in the first part of my presentation, I will show you step by step what I did with the Poland data in order to make it viable for machine learning. So first of all, what we do in every code, we need to import libraries. So libraries are generally a predetermined packages of code which we reuse later on. These packages may serve different purposes. For example, GeoPandas is for geographical or spatial data manipulations. Pandas is for data manipulations in general, and Matplot is for visualizations, and so on. You will have more descriptions in the course I will be sharing with you this evening. Okay, so what I do, I will run the code. To run the code, I'm using Jupyter notebooks. I would suggest you use the same environment. Maybe later we come up with something else, but for now we stick to that. We can run it just by pressing this button. okay, or just by Control and Enter or Command Enter on MacBook. So I'll be just pressing it all the time to show what each block of code does. So yes, so I ran it. It shows that we successfully imported the libraries. Next, what I had to do, I received a bunch of shape files with the data, and I had to convert them to a table visible for me in the code. I used GeoPandas for this purpose. And what I've done, I wrote. I won't be explaining every like line, but in general, what I did here, I converted each table, because there were tables from year 2013 up to 2023. I converted that shapefile into the readable table, added a column year to identify it, and appended it to one single table. And that is the result. You can see it below. That is how it looks like. So here we have ID or grid, which are the same. It's the grid number, and also we have our features, which are made in this way, that we have precipitation for first month, second, and so on. And then later, this is river runoff, if I remember correctly, and so on. So we have in total 6,600 rows of that. And here's a short description, and I know that this data is in grid size 0.1 degree. This all is okay, but what I need when doing machine learning, I need just a single row of precipitation, let's say, rain runoff, evapotranspiration in one column, and also feature for that month. So I have to transpose this entire table somehow to match that. This is called changing format from wide, similar to what I received, to long one. So you can see this example. So I had to convert it. Luckily, there are tools for that and some data engineering magic, and we have it. So I wrote that code, which is here, and now I have data in the format I wanted to have. So I have geometry of grid size of every grid, year, ID, month, and also values for each of the parameters. And also date is a combination of year and month. As you can see, while converting from one table type to other, we increased the number of rows to almost 80,000. In a similar way, I had to prepare grace and soil moisture data, so I can run both these cells as well. One, and then another. But the problem was that they do not match in their grid size. So the grace and soil moisture data were actually in 0.25 degree, while others are in 0.1 degree. And eventually I need to make one table. This was my target while engineering the data. So I had to come up with the solution to do that. So I also run that. I received a file of the grid, all the grids of 0.25 degrees. And I also plotted them both on top of each other. 1 second. it takes time sometimes. As you can see, this symbol of asterisk during in this braces means that the code is running. So here's the result. As you can see, we have 0.1 grid size grid in red and 0.25 in green polygons, and they do not match at all in all spaces. For example, let's see this corner. Yeah, we have 4 different 0.25 data points in here, and only single grid of 0.1. So I had to come up how to match them, match both grid sizes, and I decided to find a common denominator and just to make that 0.25 grid size into 0.05, which would then should match each other. Okay, so in order to do that, I created a synthetic grid size of 0.05 degrees using this code. Yes, I also left a column describing original geometry. And after that, I merge grace and soil moisture data to that 0.5 grid size. So I can run that just in case. Here we go. And it expanded as well, exploded the original data sets, not original, but already transformed data set, and made copies for each smaller grid or polygon. So the data frame actually increased to almost 400,000 rows. Just made for each grid, it made 25 copies of it on a smaller grid. And now let's see how the overlay looks like of both grids, 0.1 and 0.05. Patience. Here we go. As you can see, they now match exactly. Okay. There's a point in green series, we have 0.05 and red one is 0.1 grid size. So I can work with that. Both grid geometry match now. Just to make sure, I've tested whether both data sets are in the same coordinate system. They are. And now finally, I had to also join the data of grace and soil moisture with a precipitation, evapotranspiration, and river runoff. It was kind of tricky because I had to use this spatial join method, which I've never done before, but I've read some documentation. Maybe Ilya could later revise if it's correct usage, but also considering that both data sets were pretty extended, it took a lot of my laptop's computational resources to do that, and I made it a bit simple. I just made a cycle and made that join. I apologize, made that join for every date. So every year-month combination, it joined the spatial data and then saved all these tables in the result list. So the result list finally it has all tables, all spatial tables for each date. Okay, we can run that as well and see that it takes some time to do that. It's sometimes stressful to look at that asterisk and not know if it's gonna work or crash, especially if it takes a long time. But that's the work. Okay, this simple line of code, result list 0, what it will do, it will show the first data frame of first date it made a join, how the data frame looks like. So in our case, it's 2013 January. All seems correct. You can see that there are 4,259 rows. Just to make sure, we have data for 11 years and 12 months, and it should be in total then 132, I suppose, data frames saved in result list. So length method would show how many items are in this list, how many tables. If we run that, okay, so it matches, all good. Then finally, I make a union. It is a different process from join, which I was talking about. A union essentially stacks data frames or tables on top of each other. So we have data frames for each date, and this concatenation, or in more technically called union, it will stack all these tables on top of each other and make one. So that this code does that. As we can see, we have date from 2013 one, and the last one is 2023 last month, December. So far, so good. Also, I cleaned a data a bit, so I changed names of the columns. For example, I picked only lowercase. I changed to all the uppercase to lowercase, and also get rid of all unnecessary data which was generating during the engineering process. For example, there are duplicates of date from left and from right, from one and from other tables, and some others, and I just left those which are necessary. So this code does that, and in the end I also drop duplicates, which could occur during the process of spatial join, I guess. So, and we received final geo data frame. Here we are. And after that, there are two ways. One way is to proceed with doing machine learning in the same notebook, but I like to pick another notebook for that. And in order to save the data, there's of course a method to do that, to CSV. So I saved that Poland data for machine learning, and it also extracts date from my machine's system and creates this name. So I can run that as well. Let's see if that works. Sorry, I have to. Here we go. It's saved on today's date, February 7. And also this is the original I will be using. Okay. So we made data engineering, and now we're proceeding to machine learning. So, okay, here's a machine learning notebook, a short introduction here, and also description of scikit-learn library, which well, I tend to use for machine learning. There are other libraries, but in our case, I prefer using that, as generally we don't have that much data to dig into, like let's say TensorFlow for neural networks or PyTorch library, which are more tailored for that specific task. Scikit-learn is perfectly suitable library to work in our project, I believe in most cases. And the content of this notebook, the collect and prepare data. So we did that in the previous notebook. Split the data for machine learning to make training and testing sets. Selecting the model, we will select a couple of those and test against them. Then we will be training the model with the data, evaluate the data results, try a bit of model tuning using hyperparameters, and maybe make some predictions. As previously, we begin with the importing necessary libraries. So there's pandas and geopandas for data wrangling. Matplotlib is for visualizations, also as a Seaborn library. Numeric Python or NumPy is for calculations, basically. Python library for various calculations. And there's a sklearn or scikit-learn, which uses many methods for scaling, train test split, cross-validation, grid search, and so on. There will be some descriptions in the course we prepared, but also you can look them online. Just you search for documentation, which does what. Okay, and there are models. We have linear regression, gradient boosting regression, also famous random forest regressor, k-neighbors, and so on. So yeah, I already loaded the libraries. And then that same data we saved as CSV, I also converted to a table or data frame, which can be visible and workable on this environment. This snippet of code also creates a geometry ID. This line in particular, in order for process to work faster, I use it in one part of the code. So instead of looking through all polygons and going through this entire set of coordinates, I set every unique polygon coordinates to a geometry ID. That's similar to the grid numbering I received in the original data, but this is a new one generated specifically for this task, because as you probably recall, I had to downscale everything to 0.05 degrees. Okay, let's load it. Takes some time. Here we go. Well, data looks pretty fine. To evaluate our data frame and the entire data sets, there are a couple of methods in Python. For example, you can check the data types and subsets of data and so on. What I did, I created one method, which is called an analyze data frame. And it is quite long. So I didn't, usually when I work, I don't want to populate the entire notebook with these long methods, and I collect them all in one place in the end of the notebook. So I've written a few times that in order for proceed, we first need to go to the end of the document and then load this method. Like, as you can see, it's quite lengthy. What this does, It gets concise summary of the data frame, summary statistics for numerical columns, displays first 5 rows, last 5 rows, get a list of column names. This is handy in cases where the data frame has, for example, a couple dozen or 1,000 maybe columns, and you don't, it's scrolling the table is not an option, so you just get a list of all column names. They get the dimensions of the table, meaning rows, number of rows and columns. It just also displays data type of each column, counts as missing values, meaning if some values are null or none, nothing is written there, it will count you that there is a problem. It is especially important because when we are doing machine learning, not all models accept null values. And to be honest, I believe that most models do not accept. Some can handle those, but if we have some null values included in the data, we have to omit those rows in order for model to work. Or populate those non-values with, let's say, average or something like that. There are a few ways how to handle null values. You can also read about that. I think I've mentioned in the course. So yeah, it will show you that if something is missing. And also memory usage, well, maybe it's more for programming, but when if you will get more experience in Python, you will see, especially working with the bigger data sets, you will see that there are sometimes problems with that. And also a small method which rounds up some values. I also use that somewhere. Okay, so we can load this method. Here we go. It shows how it looks like. We have all the columns, their data types, also statistics of numeric values, counts, means, standard deviation, so on. Subsamples of first and last rows, column name list, shape. Again, for some reason, I put the data types and missing values per column. So we have zeros everywhere, and that is very important thing. We are good to go. Before we start, it's a good practice to visualize the data to better comprehend it. There are a lot of libraries and ways to do that. I will use two libraries, as I mentioned, Seaborn and Plotly. Both are interchangeably good. Some are better at some features of doing. So there are a few ways to visualize data. There are pre-made methods to make a quick look at make a quick visualizations. For example, count plot will count number of rows for each year. In this case, put it here. Okay, load it like that. If I want to make that count, for example, for each month, I'm missing. Yeah, there you go, for month. And if I do that for year, for date, I will get probably a very bizarre plot because we have 132 unique dates, a year and month combinations. Let's stick to the year. Okay, here we go. So the distribution of data is pretty even. Then there's a method to show a heat map. It's this visualization is called heat map. It will show with the colors and numbers the coefficient of correlation between the parameters I pass. So in this case, I pass grades data and the rest. Okay, we can load that. Maybe I won't be loading that because it takes some time from my end. It's already preloaded. Okay, shows it. Of course, Grace data will correlate with Grace data perfectly. We have one. Apart from that, we see that Grace data correlates with Q is river runoff, yes, and soil moisture pretty well in the positive matter. Not so good with the evapotranspiration and precipitation. Okay. I also like to make time series. In order to make time series, I have to first pick some grid. That's why a single grid. So that's why I picked that, created that geometry ID column. And in this case, I selected grid 6. Let's make it grid first grid and see how it looks like. And it will show time series of evapotranspiration, precipitation, river runoff, soil moisture, and grace. Okay. As you can see, the step by step, these code snippets are getting longer and longer. This is because I'm adjusting it in my own way. So I actually came up with some ideas how to improve visualizations to how I desire to see them. But you can do the same, or you can use just methods which are already created in these libraries. Also pair plots, which are similar to heat maps, but they just show the entire data set points set on diagrams, correlations of every feature against other. Yeah. Yes. Okay. Let's proceed. So we are familiarized with the data, made some pre-analytics of it, and now we proceed to machine learning. What I do usually, and I load the sample of the data frame before the machine learning, so I don't have to scroll all the way through the entire notebook and have it somewhere close to my machine learning code. First, I like to write everything in the matter so I can just select it in the easy way. How I managed to do that? By making comment and comments and comments in the features. For example, these are active parts of the features in this list, and if I comment them, commenting is by adding this hashtag before, it won't be active in this list, meaning it does not exist. In this code, it is only a comment. It is some kind of description. It's done easily with control and question mark, or command and question mark, I'm guessing on the MacBooks. So I will keep all these 4 parameters as features. Of course, target is a grace; it's not changeable. Also, making in this case a copy of data frame as data frame ML, just a copy in order not to ruin the original data frame if something goes wrong. And also, I can choose the model. So I picked in total 6 models, but I'm now showing only 4 because of the reasons that it computes them pretty long. And when I want to change something about my analysis, I just comment and uncomment and then try machine learning model. So I'm working only with two parts of the code. Okay, so I think I explained that. And finally, we have machine learning modeling, where we have, yeah, in this case, I kept as much comments as I could for every line of code. First, what we do, we split the data frame into features and targets. So we assign them to variables X capital, X uppercase, and Y lowercase. This is a common way to name those. Then we standardize feature data with a standard scaler, which, if I remember correctly, it sets average of all values to 0 and one standard deviation to 1. It transforms the data this way. Then I split the data into feature training set, feature testing set, meaning only GRACE data, then no, feature training and feature testing set, I apologize, and then feature and target or GRACE data training and testing set. I chose 20% of all entire database to be assigned for testing. So 0.2 is a unit size, but it's like the same as 20%. Okay. Also, there are splits, 6 splits. I will explain what this variable does later and write the entire code. So what this does, it takes every model in cycles in this dictionary. Yeah, it takes one by one and trains and do everything what is necessary, calculates all the statistical metrics for each model, and then prints out the results. Okay, so it begins with printing just a line of training this and or that model. Then the actual training goes, model fit. And then I try that how that model works by predicting values of train set and test set. So the one is a data on which model trained, and the other is unseen data. So we can compare how the model performs. Also, there's a cross-validation feature. Cross-validation, what it does, it divides the training set into predetermined number of splits, this number, which I, in this case, selected 6, and calculates statistical metrics for each of that split. It is important to evaluate whether the statistical metrics we received is valid. For example, if we split the training set into 2 subsets and both of them have a R² value of 0.5, we can pretty much be sure that the model is performing well because they are very, very close. But if one split shows R² 0.2 and the other 0.9, meaning that something is not right. Maybe we lack data or the model is not working in the way we expect it to be, meaning that there are very different statistical results in this case. Yes, and also in this case I calculated only R² values for training set, testing set, and cross-validation training set. In most cases, we should add at least 1 or 2 others, for example, mean absolute error or square roots mean squared error, RMCA. I don't recall. There are a few of those which are common in regression analysis. And the last code snippet is also a plotting. What I do here is I will plot actual values versus predicted, see how it fits, and also I will add a red dashed line to show how the ideal prediction would look like, and some labels and also names for the correlation plots. So here are our results. We have linear regression. The training set is in blue dots and testing set is in yellow. As we can see, this does not look too good. Something maybe to that side of positive side of force, but not entirely. Yeah, our squared values are also pretty average. Then we trained gradient boosting regressor. We have a better result, 0.69, let's say, our squared values. Not surprisingly, random forest regressor looks really not bad. So the cross-validated is 0.99 as the test set as well. Maybe something is wrong, I don't know. We should probably check it out again, but these are initial results. And k-neighbors regressor, also not bad, but you can see that the data scatter is much wider here. So we received a few plots and the statistical metrics here, and results are promising. And finally, what I wanted to show as well, we can also tune that model. In this case, random forest regressor showed the best result. I tried to boost it even further by adding different hyperparameters. Hyperparameters, they dictate how that algorithm would make the training. So there are many hyperparameters in each for each algorithm, and they all does different things. Therefore, I couldn't do that for each model. Well, I can, but I usually, in this case, I select one or two models which performs best, and then pass these hyperparameters. So we have number of estimators, maximum depth of trees in the random forest, minimum sample split, and minimum sample subleaf. What this code will do, it will only try modeling on each combination of these hyperparameters and then select the best metric, the best model which shows the best statistical metrics. It will select those automatically, and then it will show you best hyperparameters, maximum depth none, minimum leaf samples leaf 1, minimum sample split 2, and number of estimators 200. So that was my final result. And in the end, I also made a short visualization just to see feature importance. There's also inbuilt method in to see which of the features we selected influenced the result the most. So as we can see, it is Q is river runoff. Yeah, so it is had the highest impact. Okay, 45 minutes. I apologize, but I'm done now. I'm not sure. Maybe Yanis could proceed, and we will take the rest of the time for Q&A. What do you think?
I agree. I can proceed.
Okay, so the floor is yours. You take. I need to drink some water.
Okay, thank you.